Thank you very much, sir. I hope my sound is clear. So
Yeah, you are loud and
there
clear.
was no issue. Thank you very much. Now, let me go to the presentation part. All of you are aware about the number of accidents happening in our country. Unfortunately, always, hospitals are a victim. We have several cases in during the last 10 years where fire and other accidents are happening in hospitals, and a lot of people are injured. This fire due to short circuit, this is not a new phenomena in India, not only for hospital, it is quite common in a lot of buildings. And if you look at the data published by the newspapers, data published by the Fire Safety Authority, most of them claim that, for example, in Bombay, they say about 80% of fire accidents are from electricity. In Chennai, the claim is 60% is from electricity. I'm talking about the fire accidents that is happening inside buildings. So one of the study by the National Crime Records Bureau 2015, it says almost, there are about 15,000 people, those who are affected due to various electricity related reasons. And the majority of these accidents are happening in the low voltage system. Low voltage system, what I mean is, you know very well, it is less than 1000 volt AC and 1500 volt DC. So this is the this is called as low voltage. Now, what is the basic of it? It is true that electricity ignites fire. If you don't handle it properly, of course, electricity ignites fire. And what kind of fire safety measures are we doing at the moment in a building? We have life safety equipment, especially for evacuation and for the firefighters, evacuation of the people inside the building, measures for the firefighter to handle the safe installation or to handle the fire. Then we have passive fire protection measures such as methods to stop the spread of fire. The third method is active fire protection, which detects, make a warning, and maybe try to suppress the fire. And then the fourth one is a manual fire protection measure. Electricity, it's a truth that electricity ignites the fire. And the fire safety measures we know very well. The fire, life safety measures, passive fire protection measures, active fire protection measures, and manual fire protection measures. These are the established methods to handle fire. Now, about the one moment, I am trying to minimize the, about the measures, generally these measures, the above four measures, it will not stop the ignition of fire by electricity. And usage of, the above measures, for example, fire survival cable, electrical system which is able to survive fire. These are actually not fire safety measures. These are, a kind of passive fire protection measures. Use a cable which can survive the fire. That means you are increasing the passive, fire safety measure. Then what do we mean by electrical safety? Electrical safety is the measures to avoid electrocution and ignition of fire. These are electrical safety measures. So even though we use electrical safety in quite a number of places, the actual meaning of electrical safety, we should use it for, electrocution and ignition of fire. How do we do it? It is done by designing, erecting, and testing an electrical installation in a building. The design plays a major role, erection plays a major role, and the last one, testing. If all the three jobs are done properly, we achieve a very good electrical safe building, especially a very good electrical safety hospital. Now, if we look at the data, international data, if we try to compare what kind of accidents, what is the number of accidents happening in India, for example, this data is published by one of the Japanese study. It says in India, approximately 723 people are affected per year per 100 million population. In comparison, you can see, look at the other countries. In Japan, it's about 12% per year per 100 million population. This is the graph which shows how many people are electrocuted or, they are getting accident due to fire. In Japan, compared to 1949, there the average was about 600, which they reduced to 12 persons per 100 million population per year, whereas we are still standing at about 723. And with the same study, they published one more data. They tried to compare the safety score of several countries. Safety score means they have put the marks for a series of questions, and each question carry a certain mark. And final analysis shows that in India, our installations are the score which India got is 16%. Compared to other countries, you can see at South Korea, the score is 81%, and in India, I would say out of G20 nations, we are the least. How other countries are handling this? Say, for example, I took the case of three leading nations, the USA, UK, and the Germany. In USA, you know very well that the standards, the wiring practices are very, very important. If somebody violates a wiring practice, then you are out. You cannot, you will not get the electricity. And they follow the NFPA guidelines. NFPA stands for National Fire Protection Association. It's a private body, but the standards made by NFPA have been accredited or accepted by the national regulator as the national standard. Similarly, in UK, they have the BS 7671. It is called as National Wiring Rule. This is jointly published by the International Electronic, Bureau of British Standards Institute and the Institution of Electrical Technology, IET. These standards, it has got a long background. They started creating the standards way back in 1880s. Similarly, in Germany, they have the DIN VD 100 standard. Basically, in those countries, if an electrical installation is not conforming as per the standard, then you can be sure that the building owner will be in deep trouble in case of an accident. So the design, erection, and testing, it must conform the rules and regulation of these standards. Now, how these standards are originating? International Electrotechnical Commission, which is nothing but IEC, in 1962, they created the standard committee called the TC64, and TC64 created the standard IEC 364. And in 1967, the United Nations requested, or there is an agreement between the United Nations and the International Electrotechnical Commission to create a standard for the worldwide use. As a result, IEC created the standard IEC 60364. This standard is actually the basis for electrical safety worldwide. Every country, those who are following the United Nations registered country, the World Trade Organization registered country, or a country signed the agreements with these international organizations, they are supposed to follow the guidelines made by IEC 60364 for electrical safety in a building. Now, in India, the same guidance 60364 has been adopted as IS 732. Very new version has come in 2019, and we call this as Code of Practice of Wiring. As I said, in other countries, let's say for example in UK, the equivalent is called as BS 7671. Any building in UK, if it is not conforming to BS 7671, you can be sure that they will not get electricity. So confirmation as per the standard is highly important in those countries. In India, this is called as IS 732, and this is the standard which talks about design, erection, and testing. What are the parameters you should look at while designing a building, erecting a building, and testing a building. Now, out of these three things, in order to explain you, until now, I was just trying to explain you what is the background of electrical safety. Electrical safety doesn't mean you use a good quality wire or use a good quality switch or use a good quality conduit. Those things have nothing to do with electrical safety. Electrical safety means you have to design, erect, and test a building according to the latest requirement. Now let me start from the testing part. The standard recommend testing consists of, we call this as verification. It consists of inspection and testing. Inspection means we have to inspect a site, we have to check the drawings, we have to find out what are the concepts. Let's say the number one, method of protection against electric shocks. What is the basic concept adopted in a building in order to stop shock hazard. The second one, presence of fire barriers and other precaution against propagation of fire and protection against the thermal effect. This is very important, especially for fire protection. Presence of fire barriers, say for example, based on the zone, fire zone, each and every zone, once when the cables crosses the zone, we are supposed to have fire barriers. As a result of the fire barrier, fire in one zone will not pass to the other. Not only fire, fire and smoke is not supposed to pass to the other zone. And the last one here, the protection against the thermal effect. The thermal effect, in the sense, it is about the heat, how to handle heat in case of a fire. Then all the other, there are about 16 inspection points. I don't want to go much into it. Let me go to the next part, testing. Yes, the first test starts with continuity of conductors, insulation resistance of SELV, PELV. These stands for extra low voltage system, floor and wall resistance, polarity, effectiveness of automatic, starting with continuity of conductors and ending with voltage drop. There are about 10 different testings which is included in the standard. The idea is every building after erection, while commissioning or during once when the electrical system is put into service, we are supposed to do this particular testing, and every building we are supposed to ensure that electrical safety is achieved by making the inspection and testing. Now the interesting point here is, out of the 10 tests, about 4 are in supply off condition and about the balance 6 are in supply on condition. And the person who does the testing, he has to keep the sequence. In case of any failure in the test, we are supposed to redo the test after rectification. Anyway, I don't want to go much into it. Let us look at the few of the tests, only 2 tests out of this particular 10, and try to find out how we are we able to comply these tests in our buildings, especially the buildings in India. Now, these tests, for example, these 10 tests, these are mandatory for a normal building. There are installations which is special. Special in the sense, in the standards, these are called as special locations, like a bathroom in a house, a swimming pool, maybe a car charging unit, a solar PV installation, a medical location. These are special installations, and these special installations require special additional measures, additional testings are required. We will look into it, this slide later. Not only initial testing and periodic testing, both are mandatory for special locations. So basically, there is a standard which talks how to design, erect and test an installation, and I started from the last one, how to test a building, and the first test is called as continuity of conductors. What do we mean by continuity of conductors? Continuity means you have a copper wire in your building, maybe 2.5 square mm wire in your building. It starts from the MCB distribution board, it goes to a switch socket, then it finally goes to some apparatus or maybe to a fan or maybe air conditioner or whatever. In case of a loose contact, what will happen? The resistance of the whole conductor, the resistance of the circuit will be going up. If the circuit is perfect, then the resistance of the circuit is very low. And you must understand that if the resistance is higher, heat dissipated in the conductor is higher, and once when the heat is higher, after some time it will lead to insulation failure, then a short circuit, then a fire, smoke and other things. So majority of the electrical accidents happen not in the main distribution system, but on the last circuit. The small equipment are the ones, those who are creating fire accidents. So the first test is actually highly related to fire accidents, and the test is called as continuity of conductors. It is nothing but the measurement of the resistance of a conductor which you have put inside a conduit. After installing the conductor inside the conduit, we are supposed to measure the resistance and check with the available data. Say for example, protective conductors, including protective bonding conductors. Basically, the first one is about the earthing conductors. The second one is also earthing conductors, and the third one is the final ring circuits, live conductors. The live conductor means the phase and the neutral conductor also shall be tested. And compare the values with the reference. Then what is the reference? Imagine in your room or in your facility, you have a distribution board, NCB distribution board, and you have a circuit consisting of a phase conductor, let us say 25 meters, and the neutral conductor 25 meters. So totally your conductor length is 25 plus 25, 50 meters. And if we measure the resistance of the conductor, we are supposed to get a value, and that particular value is provided in the IEC standard. Let us say, for example, a 2.5 square mm wire. The reference value is 7.5661 ohm. This is 7.5661 milli ohm per meter. This is the resistance of the conductor allowed in an electrical wiring, and this is the resistance of the conductor which is used worldwide. I repeat, worldwide. This is the maximum allowed resistance of the conductor which has to be used for a wiring. Now, in India, what happens? A 2.5 square mm wire, a classic case. In IEC, the recommended value, not only in IEC, this is what is followed across the globe, including Africa. IEC recommends 7.5661 ohm per meter. So the recommended value is, I put it in the green color. There are two kind of conductors available in India. They're not two, actually, four kind of conductors. Conductor means the copper inside a wire. There are four type of copper used inside a copper wire. Class 1 means a solid conductor. Class 2 means a multi-strand conductor. And the resistance I have mentioned here, 7.41 and 7.56. 7.41 is bare copper conductor, and 7.56 is the resistance of the conductor with a tin coating. So class 2, 7.41 and 7.56. If we look at the reference value given in IEC, 7.56, that means we are supposed to use a conductor of class 2. It's a flexible conductor. Then in India, we have two more kind, not only in India, worldwide, there are two more kind of conductors available, class 5 and class 6. Class 5 is called as a highly flexible wire. This wire is generally used for panels, because inside a circuit, inside a panel board, you need a conductor because you have to twist it and you have to make a wiring through very sharp edges, turns and all. And here another problem is these, inside a panel board, the length of the wire is very short. You are not using it longer distance, let us say for 50 meters. No, inside a panel board, it may be 2, 3, 5 or 6 meters, not larger sizes. There is one more conductor available, which is called as class 6 conductor. This is nothing but the welding wire, the copper inside the welding wire, which is, very much flexible. Now, what I wanted to tell you is, the IEC recommended value is 7.56. By using a class 2 conductor, that means a copper wire, PVC insulated, maybe FRLS, fire retardant or fire survival or whatever the insulation is, but the copper in that particular conductor shall offer this much resistance. This is what is recommended in IEC and used worldwide. Whereas in India, 99% of the installations, class 2 conductors are not used. We use class 5 conductors. You can look at the chart in IS standard, IS 8130. Class 1, class 2, class 5, class 6 conductor values are given. Now, class 5 conductor. We use class 5 conductor in India. Why we use class 5 conductor? Because it is little bit cheaper compared to class 2. Class 2, say for example, class 2 is about 7 to 8% expensive than class 5 conductor, because the copper, as you know, if the purity is higher, the charges, the cost is higher. Class 5 conductor, most electrical accidents in buildings happen in the final circuit. Often conduits are filled with wires. What I mean to say is, you know very well, we have, let us say, an 1-inch conduit, and inside the conduit there are filling factors. You are supposed to fill it maybe 30%, 40%, not more than that. Whereas most of the conduits in India, it is completely filled. So once when the current flows through this particular conductor, it produces heat, and the filling factors are defined in order to ensure that the heat produced in the conductor are handled very well. all the derating factors are based on class 2 conductor. Whereas in India, we don't use class 2 conductor, we use class 5 conductor. Since we use class 5 conductor, the heat is about 7 to 8% high, because the resistance of the conductor is about 7 to 8% higher in our wires. In a single phase circuit, a line conductor going and the neutral conductor coming back, approximately 16% higher heat dissipation will happen in the conductor in the single phase in a single phase circuit. What it happens? 16% higher heat means, higher deterioration, higher degradation of the insulation, and finally fire. Internationally, class 2 conductors are used for wiring. Indian buildings will fail if the test is carried as per the IEC standard. What I wanted to mention here is Indian buildings will fail if the test is made as per IEC standard. If somebody, maybe an international company, they wanted to do a test saying that I am coming from UK, I wanted my Indian building to be equal to my building in London, and if they try to test the Indian building, you can be sure that the building will fail. So wires with class 5 conductor increase the chance of accident, higher heat dissipation, degradation of insulation due to higher heat. But the most important point is not the heat. The most important point is higher fault loop impedance. Fault loop impedance means you have a protective device to trip your circuit. The tripping mechanism is related to the current, the fault current which is flowing through the circuit, and the fault current flowing through the circuit is related to the impedance of the circuit. If the impedance of the circuit is higher, fault current is lesser, and most often your circuit, the protective devices will not trip. Let's say, for example, an MCB, you have an MCB, but the MCB is not tripping because of the higher impedance of the circuit, and that leads to fire. So non-disconnection of the supply lead to fire due to short circuit. Now, the test number 6. This is all about the first test. Let us look at the test number 6. The test number 6 talks about automatic disconnection of supply. Automatic disconnection of supply is very simple. In case of a problem in a circuit, the supply should trip, and you have devices such as ACB, fuse, MCB, MCCB, ACB, and these devices are called as OCPD, overcurrent protective device. And most of these devices, it has got a tripping curve in this particular picture. On the x-axis, you can see 1, 2, 3, 4 up to 30. This is the multiples of rated current, and on the y-axis, the tripping time in seconds. Say, for example, you have a type C MCB. You have an MCB, type C MCB. Now, one of the first job of the standard is within what time, or to declare the time with which the automatic disconnection should carry out. Say, for example, in a normal case, something about here where my cursor is moving, I will put it on the pen. So somewhere here, within this particular time, the MCB is supposed to trip in order to achieve safety. This time means something about, let us say, 0.17 second in case of a 230 volt supply. Now imagine you have a type C MCB. The approximate current required for the MCB to trip is something about 10 times. A 63 amps MCB requires 630 amps to trip. The fault current shall be minimum 630 amps to trip. Similarly, if you have a type D MCB, because in a type D MCB, the current is not 10 times, it is 20 times. So 1200 amps current is required to trip the MCB. What I wanted to tell you is the disconnection time of a protective device is highly important in electrical safety. What does it mean is you have a device to trip, and that particular device is supposed to trip within a specific time, not after a few seconds, after a few minutes. That is illegal. So it is supposed to trip within this particular time in case of below this particular time in case of a fault. Now, here you have a source, you have a load, and this is the fault. Imagine there is a fault in your load, there is some short circuit, or there is some earth fault in your maybe an UPS or maybe a circuit. The fault current is flowing in this closed loop, starting from the transformer, coming through your protective device, through the device, it goes back to the source. This is the current loop, and the impedance of this loop determines the, imagine you have a 63 amps type CMCB and the impedance of the loop is 4 ohm, then the current is only 63 amps, your MCB will never trip. Now in the second case, if the impedance is 0.4 ohm, then the current is 630 amps, your circuit is safe. So what does it mean? In IS 732 in 1989, not today, 31 years back, included a test called fault loop impedance test in the standard. During design, we are supposed to measure, we are supposed to calculate the fault loop impedance in the circuit. After commissioning or during installation, after installation of the transformer, because this is a line, this is a live test, you require the source. So after installation, immediately after installation of the transformer, you are supposed to make a fault loop impedance test, calculate the fault current, check with the rating of the MCB and find out the MCB is tripping within this particular time. It has been included in the standard in 1989, but even in 2020, it's very difficult to find out buildings where such tests are made. Now, another approach for safety. There are two approaches. In the design, there are two approaches. The first approach says, in case of any problem, automatic disconnection of the supply is the solution. That means in case of any insulation breakdown, your MCB should trip. In the second case, continuity of supply during the first fault. What does it mean is, you have an insulation failure in your building. There is one insulation failure in your building, but the supply shall not trip. So the method to handle the first case and the second case is, the concepts are entirely different. The first case we use for a general application, and the second case we are supposed to use for special application. Say for example, operation theaters in hospital. Because imagine there is an operation theater and some activity is going on, and if the incoming MCB trips, what is going to happen. This will become a disaster. So for certain applications, disconnection of the supply is dangerous, and for those applications, continuity of supply is highly important. So as I written here, this is the continuity of the supply. There are two approaches, and in the first case, safety is achieved by protective equipotential bonding. I don't explain much. And the first one is called as earthed supply, and the second one is called as unearthed supply. Here, this is called as earthed, and this one is called as unearthed. We also, people, those who are there in the hospital sector, they know IT supply for, especially for the operation theater, or especially for the certain activities. Unearthed supply is also used. There is an isolation transformer. Secondary side of the isolation transformer is not earthed, and there, insulation monitors are used, and you achieve a safety measure called as continuity of supply during first fault. So these two are the basic, the concepts. Now, when we go look at the concept earthed system, whenever we listen to the word earthing, then immediately people think that earthing means you take a wire and connect your system to an earth pit in soil. As a result of this concept, what we do, transformer neutral, we have two connections to earth pit. Transformer body, we have two more, then two for the main distribution board, two for the lift, each lift, two for UPS, two for lightning protection system, and two for maybe medical equipment. And there are hospitals with more than 100 earth pits, 100 to 300 earth pits all around the hospital. And some earthings are, few are chemical earthing, few are digital earthing, few are pipe-in-pipe earthing, few are, having some special things. I don't want to go into the detail of those things. Actually, earthing has nothing to do with these earth pits. Earthing is a subject which has nothing to do with these earth pits in low voltage engineering. In low voltage engineering, the method of earthing is totally different. What do we mean by earthing in low voltage? Means this is, as I said, I repeat again, making separate earth pits under the soil and probably interconnecting everything under the soil is a big mistake. you don't need it. It's a misinterpretation of the standard and regulation. Now, how do you do that? You can see this picture in IS 3043, picture 38 to 42. You can see the same picture here. On the left side, you have on this side you have the engine, prime mover, and this is the alternator. This is actually a generator. The generator body is connected to an bus bar, earth bus bar. The neutral of the generator is connected to the same bus bar. Incoming EB supply is also connected to the same bus bar. Outgoing side, load side electrical apparatus is also connected to the earth bus bar. And now this bus bar is connected to extraneous conductive part. Extraneous conductive part means the metallic parts in a building, such as air conditioner duct, the fire pipe, metallic fire pipes, the metal reinforcements, and so on. So then the bar is also connected to an independent earth electrode. Of course, don't get taken away by this word independent earth electrode, because earthing here, the symbol, this is called as a chassis earthing. This has nothing to do with earth pit in soil. This is a totally different concept as such. So this is the correct way of earthing. Earthing, again, I repeat, in low voltage engineering, the earthing, please don't take away that earthing means something in soil. Earthing has nothing to do with in soil. And what is more important is the kind of earthing system. There are earthing system called as TNC, TNS, TNCS, TTIT. There are, these are something like, these are the type of wirings which you are supposed to follow. And this is much more important than the earth pit. Earthing of an installation. What do we mean by earthing? It means, number one, you have exposed conductive part. Exposed conductive part, imagine these are the metal body of current carrying equipment, such as panel board, such as electrical apparatus, such as UPS, such as motor, and so on. Now, in the installation in your building, you are supposed to have a main earth terminal, item number B. You have the extraneous conductive parts, such as structural steel, for example. Then you have a metallic water pipe. Then you have a TT and an earth electrode in case of a TT system, and then you have a TN system. TN, this dot means this is the neutral of the transformer or neutral of the DG. And the first one, this is called as protective earthing. Protective earthing means connecting all exposed conductive part to the MET of the building, and connecting extraneous conductive part to the building. This is called as protective equipotential bonding. And the last one is called as measures for automatic disconnection. And here, item number 4 is called as supplementary bonding. I go into it detail in the next slide. And say, for example, earthing in low voltage system. What does it mean? Fault protection is achieved by a safety measure called as automatic disconnection of supply. Automatic disconnection of supply is achieved by protective earthing, protective equipotential bonding, and automatic disconnection of supply within the specified time. So if you read a book, if you read any standard or a technical book, you will only see automatic disconnection of supply. You will not see the other three, because it is understood that if anybody says automatic disconnection of supply, automatic disconnection is achieved by protective earthing, protective equipotential bonding, and automatic disconnection of supply. These are actually very well explained in the standard. Then what do we mean by protective equipotential bonding? It means at the origin of the installation, that means at the main distribution board, this is the earth bus bar of the main distribution board. You have different metallic installations such as metal firefighting pipe, sewage pipe, HVAC duct, structural steel, and so on. We are supposed to make an equipotential bonding at the main distribution board, and similarly one more protective equipotential bonding at the sub switch board. And here the first one is called as main equipotential bonding, second one is called as supplementary equipotential bonding. Now once when we come to a hospital environment, supplementary protective equipotential bonding is highly important. That means, imagine you have at the 5th floor, you have an operation theater, and at the operation theater, between the electrical apparatus, between the medical equipment apparatus, between the metal pipes, metal gas pipe, metal oxygen pipe, or maybe the wash basin or other structures, everything we are supposed to make an interconnection. Why this is important? Because you have a patient who is maybe under treatment. The basic safety electrical resistance, it is offered by the skin, and most of the cases, electrical apparatus are bypassing the skin, and sometimes the apparatuses are very close to the heart or in the artery. In a hospital, the basic safety to be performed before installation and after every repair are earthing integrity. That means the resistance of the resistance. Please understand, this has nothing to do with the resistance of the earth pit. This is the continuity resistance of each and every bonding. And then earth leakage. These two are highly important. Why? Because a current flow through the heart is, it will create a micro shock, macro shock, and the problems such as due to magnetism and self-inductance, even a wet floor is enough to create a shock. These are actually special things. Actually, this has nothing to do with the fire, but this has very much to do with the patient safety. Electrical safety not dependent on voltage, but on the current. At low voltage, leakage current flow through the body may be fatal. Patient may be connected to several devices simultaneously, and patient may be connected to conductive electric circuits such as ECG apparatus, and contact directly to internal tissues are also often made. Now, one moment. The patient may not be in a condition to react to an electric shock because he is a patient. Electrical resistance of skin, which is normally an important measure, because the resistance in the body is offered by the skin, and most cases in the hospital this is bypassed. Medical electrical equipment may often be used to support or substitute vital body functions, and if it trips, then this creates another problem. So why this is important? The electrical safety in hospitals are important. Electrical and electronic system design in healthcare facilities is extraordinarily challenging because it requires a lot of skills. You must know what are the basic safety measures. You must know what are the electromagnetic problems. You must know what are the voltages, currents, those who are going to flow, the frequencies of which is going to influence, and it's a highly technical job. I don't want to go much into detail. Now you can see these details in the National Electrical Code, NEC 2011. NEC 2011 has introduced about 13 different kind of protective measures. Say for example, P0, duration of touch voltage restricted to a safe limit, TNS, TT, IT, this is the electrical wiring system. And let us look at P2 as P1, but additionally resistance between extraneous conductive part and the protective conductor bar of the room not exceeding 0.1 ohm, additional to P1, supplementary equipotential bonding. Actually, what I shown in the previous picture is supplementary equipotential bonding. This is what I wanted to explain to you. I don't want to go into the details of each and every safety measure. Then the National Electrical Code also had divided the different kind of application, different kind of utilities in the building, and each utility area, what kind of measures are necessary, these are specified. Let me skip this. Medical locations. Yeah, in a group 2 environment, group 2 means, in an operation theater, the vicinity which is close to the patient. The safety topics are supplementary equipotential bonding. This is the first protective measure. What do you mean by supplementary equipotential bonding? This means you have a different kind of metallic things, metallic objects, including your equipment, including your maybe the table, or maybe the wash basin, the pipes, and so on. Every metal part in that location shall be interconnected in such a way that the potential difference during the normal operation is, or during the normal case, it is lesser than about, I think, 20 millivolt or 30 millivolt, very, very small value. Isolated supply is required. Now, patient environment. The first safety measure, what I want to tell you is, this is called as equipotential bonding, protective equipotential bonding. Now, let us go to the test. The additional test which is recommended or which is made in almost every country for medical location is number 1, functional test for insulation monitoring device and medical IT system. and the acoustical visual alarm system. That means you have a medical IT transformer, which the secondary side is unearthed. That has to be tested. And the second test, you please read it, measurement to verify that the supplementary equipotential bonding is in accordance with these clauses of the standard. I didn't produce the clauses of the standard, but the supplementary equipotential bonding is the second test. And the third one, verification of integrity of the facility required with this particular clauses of the standard for equipotential bonding. So everywhere the standard is talking about equipotential bonding. That means all metal things in your building shall be connected together so that there is no potential difference between different kind of equipment. And the periodic testing, the functions, the different kind of periods are also made in the testing. Now coming back to this particular area, supplementary equipotential bonding, I made a statement that every apparatus in the equipment in the hospital shall be interconnected together. What do you do for a medical equipment? A sensitive, highly expensive equipment vendor will come and tell you, no, my equipment is very special. If you connect, I need a separate earthing. It's always a claim by the manufacturer. I need a separate earthing. As a result, the management or the engineers in hospital, in most of the hospitals, they put or they connect the electrical, the sensitive equipment to separate earth pits. As a result, what we are doing is we are violating these requirements. The protective equipotential bonding conditions are totally violated. Actually, it is wrong. Challenges. Fallacious ideas. Equipment manufacturers ask for special requirement that always they say, I want to separate because I have several sensitive issues. My equipment is the best in the world. My equipment is so sensitive. This is actually a wrong idea. And when we talk about the safety, people always say, oh, so we have a device, probably this device didn't trip, so you replace the device, you put a new device and you achieve electrical safety. This is also wrong. Electrical safety is often understood as install a modern product by which you get a safety. Say, for example, you use a good quality wire, not a class 5 wire. Always the wires are class 5, but people say instead of FRS wire, you go for FRLS wire. Basically, play with the plastic in the wire. Then you install an RCD, you install special breakers and special earth pits, and these are generally, termed as improvements in electrical safety. Actually, this has nothing to do with electrical safety. Electrical safety is often used as a marketing tool by the manufacturer. A new product, people say, oh, this is going to increase the electrical safety. And what is happening, unfortunately, is the installation standards. Installation standards means there is a way to design, erect, and test the installation. Most often, the installation standards are neglected. What do we do? First, we should understand that fire detection, fire suppression, compartmentation, fire sealants, smoke extraction, all these safety measures, of course, these are very much highly essential for a building, but these measures will not stop ignition of fire from electricity. And the separate earthing of sensitive equipment is an additional problem. 90% of ignition of fire from electricity could be avoided if the installation is designed, erected, and tested as per IEC 60364. I have explained you two cases. The continuity of the conductor, that means the test number 1, resistance of the wire, and the test number 6, fault loop impedance test. As I said, these two tests, there are 10 tests. Out of 10 tests, the most important 2 tests are not at all carried out in most of the buildings. And if these tests are carried out, for sure, the design has to take care of it, the installation has to take care of it, and 90% of ignition of fire can be stopped. And the second part is high degree of electrical safety in patient environment can be achieved only by implementing additional tests. Additional tests, as I said, the equipotential bonding. Now, if the equipment vendor comes with a claim that I need a separate thing, actually, please don't do it. It's wrong. What can we do? After, this is my webinar for hospital. Maybe this is 25th or 26th for exclusively for hospital. Generally, I make it for 3 to 4, 5 hours. Today, due to the time, it's very short. After my webinars, a lot of people ask how to make the improvements, and so what we do is we advise the people how to make making small sketches, making small drawings, and tell them how they can improve their installation as per the IEC standard. Of course, we do it free of charge. This is not commercial thing. Then the first one we do as free. Then they will come back saying that the equipment vendors are not agreeing to the requirement. Then we have to have a bigger discussion with the equipment vendors, convince them, and finally make them understanding about the safety dangers behind the separation, and we are able to convince a lot of manufacturers, and they finally agree. And the third point which we do is the preparation and submission of documents to clarify and improve misinterpreted subject by the authority. What I mean to say by authority is the electrical, maybe sometime the electrical inspector, they will say, I want 2 earth pit for neutral, 2 earth pit for body, 2 for DG, 2 for DG neutral, and so on. Actually, these are, as I said, this is wrong. This is never written in the standard. These are misinterpretation of the standards and regulations. So we also make support the client in discussing or making such things perfect, and also do inspection and testing. So this is all about the safety. Thank you very much. I hope we can go for the question and answers. Over to you, Pradeep sir.